Should you just start the recording from the beginning?
Don't worry, I'll just delete the first part.
Okay, good.
Okay. This is the expression that I've been describing to you just now. Sigma, rho, beta, these three are constants. These constants are determined by the weather system or whatever system that these equations are used to describe the properties of them. So you can choose them. Once you choose them, you solve this equation numerically. But today, we're going to try to solve this analytically. And first, I'll show you the results. This is a numerical plot using Xcode or other computer numerical solving software to solve it. That's actually a three-dimensional plot. The dot here is one attractor, the dot there is another attractor. So if you throw in a particle and let it evolve dynamically, let it follow the force in this system, it will just go on and on like that. And the shape is a butterfly shaped. So if you project this 3D image onto the XY plane, what would it look like? It would look like this. Sorry about this, it's a little bit too dim. So actually, it's not just one big loop. There are thousands of dimmer loops inside as well. So it would really look like a butterfly if you project it on XY plane. Same thing would happen if you project it on XZ plane and the YZ plane. By the way, if you try to draw a diagram of X versus time, it wouldn't look like a butterfly, but I didn't plot that. It's not important anyway. It would look like that shaped, and then goes down, and then goes up, and then goes down. It's a periodic function, that's all that is important. And in this case, you can see very clearly that this is a periodic function. One period would like that, when it finishes one loop, the particle will just carry on another loop, which is probably a little bit smaller than that, not exactly the same, but the shape is very similar. The thing I need to point out is, this Lorentz system is very sensitive to initial conditions. There are three plots here. I'm going to explain to you what they mean in a second. So if you just, I really need to describe this to you. So there are yellow lines here. This is a snapshot of the system at time t is equal to 1. There are supposed to be two lines. One is yellow line, one is blue line. You can see the blue lines in those two pictures very clearly, but not in the first one, because the blue line and the yellow line coincide with each other in the first line. In the first snapshot, and the blue has been covered by the glowing yellow color. We can't see it, because all you need to notice in the first one is the blue and the yellow coincide really well. In the second, they don't coincide that well, so you can see blue glows from place to place. In the third one, really half of them is blue, half of them is yellow. What is going on here is this. The figures I showed you just now are 3 time segments of the 3D evolution of 2 trajectories. One trajectory is the blue, one is the yellow. So what happens is I throw in a blue particle, I throw in a yellow particle at the same time, and let them evolve. The difference between the blue and the yellow particles is they have an initial position difference of 10 to the power of minus 5, which is extremely small, and y and z axis are the same. They're just different in x direction, but tiny separation between them. However, as you can see, the difference that this tiny initial difference resulting is huge. If you see it again, that's at time t is equal to 1, whatever unit is in. These two particles pretty much follow the same projectile, but when time evolves, they start to diverge, and just when time goes to 3 times that amount of time, you can really see that the two particles are following almost completely different trajectories. So how the system evolves is very sensitive to initial condition, how the configuration is like at the beginning. That is one property of this Lorentz attractor. If you remember, when I showed you those 3 differential equations, there are sigmas and rhos and betas in the equation, detailing or specifying what the system configuration is like. And the crucial one is rho. For small values of rho, the system is stable and evolves to one of 2 fixed point attractors. Let me see what that is like. So this is for a small rho. Rho is equal to 14 and rho is equal to 13. Both of them are small. One is big. More than 24 is big, it turns out. So this is one attractor. The particle just fall into this attractor. But actually, I guess that I understand this as two particles. Both of them are green. One particle goes to there and ends up there. The other particle goes to there and ends up there after some trajectory. And same with that. The particles will just end up there instead of doing crazy things like wind around and around and around. However, let me go back to the previous slide. When rho is larger than 24, which I'm going to show you soon, the fixed points become repulsors. Those two attractors become repulsors, and the trajectory is repelled by them in a very complex way, evolving without ever crossing itself. So the particles would get forever closer to the particle, but when it gets closer, it will just be repelled, and then current, this periodic behavior just goes on and on. Which is, in this diagram, where rho is equal to 28, which is bigger than 24, we've got three particles here, red, green, and yellow. Throw them in and let them evolve. It turned out that they would just do this instead of settling down into the 2 points. This is for rho equal to 15, which is smaller than 24. That's the second property of Lorentz Attractor, the value of rho. And that is how you do it. You write a code and then let the computer calculate it. Today we're going to solve this analytically. That is our original expression, but we're going to pick one to work with. Notice that we have chosen rho is equal to 28, meaning that those are really strange attractors. They don't just behave like the value that falls down to the bottom and stays there. It's not as boring as that. It's going to have some funny features associated with it. And sigma and beta are just two other parameters. And we've chosen them to be 10 and 8/3, which are two very typical values people work with. As all other differential equation systems, there is no way, what physicists normally do is to propose a trial solution instead of just integrate it, because you can't really integrate it because this is x on the left and y and x together on the right. So you've got to propose a trial solution and hope that the trial solution would work. If it works, then this trial solution is the only trial solution that you can find for this differential equation system, because according to uniqueness theorem, which states that. In this paper, the authors were talking about singular solutions. I have no idea what it was. I checked out on Wikipedia. It says, a singular solution of an ordinary differential equation, which was the differential equation I showed you just now, is a solution that is singular. So, what is singular? If you have y is equal to 1/x, you can't have x is equal to 0, because that would explode the expression. We say that this expression, or this, is singular at point x is equal to 0. That is what it means by singular. Or one for which the initial value problem fails to have a unique solution at some point on the solution. If you don't understand this, don't worry, because it's very technical. I have to say that I don't understand probably either, but I have to show you this because this is a very important point. In this paper, the authors are looking for singular solutions instead of other solutions, because that's the line of attack when you try to solve a really nasty differential equations system.
I mean, it's fine because it's actually very straightforward. You're just looking for solutions which include cases where the function goes up, so it is not differentiable everywhere. It is not defined everywhere.
It's not defined everywhere, that's true.
So you're just looking for some interesting solutions.
Yeah, I think that's what it means, but I never approached this very formally. Yeah, I think Chris is right. Because it just focuses on singular solutions and not anywhere else. But let's move on. You can propose lots of different trial solutions. Physicists normally propose exponential, but in this case they propose psi series solutions of the Lorentz system. The definition of psi series is this: a logarithmic psi series centered at t0 is a series of the form this. So it's a sum of a polynomial times an expression to the power of n, where n is just a number, it's just a constant, an integer. And this eta is a logarithm, and the b is just a constant, another constant. And each Pn is a polynomial in eta, in the definition of the eta. So that's how you define eta, right? B is a complex number with its length modulus being 1. And in this case, we choose b is equal to plus or minus 1. We can choose other things, but this is the simplest case, so we choose b is equal to plus minus 1. So this is the proposed solution, and we plug this in and hope that the result will come out, which will work. If you look back at the original 3 differential systems, you will see that those are just x, y, z, and t, and there is no, mathematically, I'm not talking about physics, mathematically there is no reason that y, x, y, and t, and z cannot be complex. So in this case, they have, for this moment, forgotten about physics and use maths to do this, so they are looking for complex solutions for t and x, y, and z. And when they finish this calculation, they discard the complex part and just focus on the real part and interpret what it means when you have a complex time in the end. So sometimes you just can't do solutions, just can't do maths without complex numbers. So in this case, they have extended all the 4 variables into complex space. Sorry, this expression, when you write it out, it's like that. For x, we start from m is equal to minus 1. Sorry, I've got to go back again. So start from this thing, n is equal to minus 1. From minus 1, 0.
Oh, it's just the Lorentz series.
This is a psi series, not quite Lorentz series, is it?
Lorentz series in complex analysis.
Probably.
You have the minus first element, which would be like the residue.
Right.
Isn't it?
That is it?
But p is some log, right?
Yeah.
Yeah, this is some log. If I go back, you probably need to remember this if you want to understand it later better. The p is just, eta is log. Eta is the argument of p, and p is just a polynomial. When you sum up from minus n to infinity.
Okay, so just Lorentz series of this p, isn't it?
Lorentz
Yeah,
series.
because if you differentiate that, if you have a negative power, then you get the log. If you get natural log, not just log.
Okay.
How does it look? This is series.
So minus 1, 0, I think I've left out a term, let me check.
Aha,
Yeah.
that happens already when you plug in the solution.
Yeah, no. I haven't plugged in yet. This is just the proposal. I haven't plugged this in yet.
So what's the relation between x and psi?
X
X, y, z, and psi.
and psi. So this whole thing is called psi series, and x is equal to this series. So that's your trial solution. There are many variables that you haven't found out yet. For example, what is this eta, and what is this p polynomial going to look like? You have no idea.
It just looks, because you proposed psi, and I was wondering what is the relation of psi to x.
So you're just saying that every function can be expanded as a series, then?
Yes, that's true. So x is
No,
equal to the
finding them.
psi series. That's what this means. And
So we assume that x, y, z are all psi.
so they're all psi series, and x is equal to that with p a polynomial, and y is equal to that. Q is another polynomial. This is just
Yeah, and r is another polynomial.
Yeah.
Why doesn't x have a -2 component then?
I don't know. In this paper, they don't have a minus 2 component. It starts from minus 1, and the other two starts from minus 2. It's really strange because they should be symmetrical, right? There is no way x-axis in space is not symmetrical to y and z-axis, but that's how they did it. Let's just bear with it. I don't really understand. And apologies, I left out the terms p0, p1, p2, same with that, but doesn't really matter here.
So,
I just pointed it out.
When you've got p sub 2, does that just refer to the 2 in the term in the series and not to
That's
the
the
word?
second term. That is
Yeah, it's
It
two
doesn't
just
tell
I
what the
mean
series-
just denotes this the second term.
Okay, so it doesn't tell you anything about the order of the
No,
polynomial.
it doesn't tell anything. I'm going to plug this into the original differential equation.